Thanks a lot, Victor. Hello, my dear colleagues and friends. I'm happy to be here to see your bright faces. And let me introduce this research, as it was mentioned, polarization microscopy, biomedical imaging, and diagnostics. My name is, My name is Yuri Yushchenko. I represent Chernihiv National University from Ukraine. So today we will have a lecture now. And on February 23, we will have a laboratory experimental demonstration here, just here, so everyone can see and can measure everyone I will talk about. So the list of lectures, it will be one lecture, but 4 directions, including the introduction, is the following. The lecture first is a basic concept of polarization, Stokes vector, Mueller matrices itself, and basics of laser polarimetry. In the second lecture, we will discuss some basics of model description of structure and optical anisotropy of biological tissues. On the third lectures, we will talk about the methods and resources of analysis of obtained results during the processing of biological tissue polarization in homogeneous images. And on the fourth lecture, we will discuss the principles and methods of polarization and Mueller matrix mapping. So a few pictures of our Chernihiv National University main building. Someone saw it before. Someone, I hope, will see it in the near future. So it's our main building. Rector and vice rector are here now, I hope. This is another view of the university. It's a central entrance. Everyone can see. This is a church, because this university was founded on 1864, I think, by the law, by the talk of Emperor of Austro-Hungarian, Franz Joseph. Here, some view of our town. It's a main street. You can see this Austrian-Hungarian type, just a little bit German type buildings. Here, our theater and the view from the top of Chernihiv town. So let's start with an introduction, and we are trying to formulate some basic concepts of what we will talking about. So the first concept is that why we are dealing with the optical methods at all. So optical methods of diagnosis of biological objects itself and the visualization of the structure occupy now a leading positions thanks to their high information content and capacity also, and multifunctional capabilities. So you will know about the photometric methods, spectral methods, polarization itself methods, correlation methods, etc. What should be stated is that a new scientific direction within optics at all is now formed. It's called optics of biological tissues and fluids. And this direction is a rapidly developing thing. The main areas of basic research are the results of theoretical and experimental studies of photon transport from the very beginning in biological tissues and fluids. After that, separate direction in optics of biological tissues and fluids formed by polarimetric investigations. It should be stated that analysis of polarization characteristics of the scattered radiation allow us to obtain additional quantitatively new results on morphological and physiological state of biological tissues. A new step, you maybe know about it, lies in the development of methods of optical diagnostics of biological tissues. It deals with the fluorescent techniques and the analysis of polarization state of these fluorescence techniques. So-called laser fluorescence polarimetry or laser autofluorescence polarimetry. Let's start with the light. You know that the light, it's an electromagnetic wave. The electric vector oscillates in, here you can see, in the X plane. Magnetic vector oscillates in Y plane. And the number of way of propagation is along to Z axis. In optics, we deal mostly with electric field itself, because magnetic field is some other very wide research of area of research. So let's consider the electric vector here, this one. So here you can see it yellow. It can be decomposed on a two orthogonal projection, E sub X and E sub Y. These are two plane waves. You can see the equations of these fields here. It's an X component of our electric vector oscillation and Y component of our electricity vector oscillations. It differs by these amplitudes, and here the initial phase are also presented. So, you know, the omega, it's an angular frequency, K, it's a wave number. So, and this is a very important thing, that a phase, initial phase. The initial phase, yes, it's a time from the beginning of oscillation. As you can see in this figure, what is the initial phase? 0, yes, exactly, 0. But a little bit later, we will discuss it very precisely. So what kind of parameters do we, or can we use in order to make some diagnosis or make some quantification of, for example, scattered light? Due to this representation. Amplitude can be used for some evaluation. Yes, maybe. Frequency also. Phase, including the initial phase. And the fourth parameters I'd like to present, it's a polarization. Who knows about polarization? What does it mean? Yeah? Exactly. It's a trajectory of the tip of this vector when we see like here. Cool. So, about the polarization and the importance of these parameters and the possible realization of diagnostical methods. So, what was said, it's an important property of electromagnetic waves. For example, in communication, completely polarized waves are used. In radio astronomy, unpolarized component exists. And the technique to analyze the polarization known as polarimetry. When we deal with the laser radiation, called laser polarimetry. The complete polarization types of electromagnetic waves are the following. It's three types: linear polarization, circular polarization, and the most common type is an elliptical polarization. Due to the radio astronomical sources, they may possess random polarization, also known as unpolarized waves, and the partial polarization. It's a sum or a mixture of completely polarized and completely unpolarized radiation. So it's a very complex situation, so we are not talking about it. So we will, on this lecture, we will deal with classical complete polarization types. Let's start with the graphical representation and the so-called polarization ellipse. So as we just talking, so the polarization is a trajectory of the tip of electricity vector here when we are looking in this direction. So when we analyze these two orthogonal components of the electricity vector and do some algebra, it can be done by itself. So we can obtain this equation. It's a squares, yeah, sine, cosine, and so on. This is well-known equation of the ellipse. Let's start with the parameters which this ellipse can be characterized. First one is the size of a minor axis. Minor axis, semi-minor axis. The size of major axis here. And semi-major axis also oftenly used. The third very important parameter is the orientation, so-called tilt angle or azimuth of elliptical polarization. Between this direction x and the semi-major axis. The fourth important parameter is the axial ratio, so-called ellipticity of polarization. It is the angle between, let me see, yeah, between the lengths of the minor to the lengths of the major axis here. It can be plus or minus, yeah? This is ellipticity angle, very important parameters. Also, it can be used as a diagnostical parameters. It's a sense, clockwise or anti-clockwise. So, you know, this electricity vector, why we obtain ellipse, it's sensing clockwise or anti-clockwise, while wave is distributed forward. On this slide, you can see the most easy and the most conventional type of polarization oftenly used in different investigation. It's a linear polarization. It should be stated that any form of complete polarization resulting from a coherent source can be analyzed using the polarization ellipse. For example, for this one, yeah, these two projections. So if there is no amplitude in y, this one is equal to 0. So there is only one component exists, is x vertical, yeah? If we can return one slide. So when you here place y, yeah, or x is 0, so we will obtain simple like this oscillation in this direction, in x direction, yeah, and in x plane. Here's the propagation direction. It's like the projection of this oscillation on this plane will be linear. Or if there is no amplitude in x component, there is only one component exists, it's y or y component, yeah? This one. So for this oscillation, always said it's a linear polarization with azimuth is equal to 0 here, with azimuth is equal to 90 degrees. For example, for the plus minus 45 degrees azimuth, the phase difference between of these two oscillations or these two orthogonal projection of our electricity vector should be 0 or pi for plus and for minus. And the ratio between these amplitudes, they must be equal. So they are equal, and the resulting oscillation we can obtain here with plus 45 degrees azimuth or minus 45 degrees azimuth. So let's start with another case. So it should be noted that linear and this one circular polarization, it's a boundary states of the most common elliptical polarization. So if we have our well-known two projections, yeah, and if the phase difference initial, yeah, this delta, is plus minus 90 degrees, and we have this ratio of equality between of these two components, then this ratio is equal to cosine, and this ratio is equal to sine, and we get the equation of a circle itself, yeah, with a clockwise or anti-counterclockwise, yeah, rotation. And this wave is said to be circularly polarized. Yeah, you can see it here. This is a procedure of adding of these two orthogonal components. And if we will look here in this direction, we will see circle. Here you can see the procedure of adding of these two components. So we call the phase difference is plus minus 90 degrees, but the phase shift is equal to quarter wave between of these two oscillations. And when you will do summarization of this vector, and after that this and this, the tip of your summarized vector will be rotating. Here, this is. Okay, let's continue with elliptical polarization. So, in the most common case, the magnitudes of Ex and Ey are not equal. And there exists a phase difference between the two. In this case, the tip of the electricity vector describes an ellipse, and the wave is said to be elliptically polarized. Here, you can see these two oscillations, these two projections, yeah? The amplitude is not equal between each other, and there is some phase shift, not 0 and not 90 degree. Okay, and in this case, in this direction, we will see ellipse. Due to the ratio between of these magnitudes and the value of this shift, phase shift, the rotation could be clockwise or anti-clockwise. Here you can see it. So, linear and circular polarization, when we can add it, gives us elliptical polarization. And you should know that any wave may be written as a superposition of the two polarization. Let's see some interesting program. You can download it freely through the internet. It's called Emanim. So if we have a linear polarization, yeah, this one. If we have another linear polarization, this two wave, what should we obtain when we add one to another? Okay, yes, exactly. We will obtain also linear wave, but in this direction, this blue one. Okay, another interesting question. What should we do if these two waves, or a projection of one wave, yeah, will be left and right circular? We obtain exactly, because the amplitudes are equal, the phase difference are the same, 0. So let's try to, okay, show axis only, yeah? This blue one and these two vectors are rotating. Okay, let's continue with as we said a few minutes ago that elliptical polarization is the sum of linear and the circular one, yeah? Let's check. Let's check. Yeah, this one, yes? Yes, you can see it. And what we will obtain, for example, we talked about when the amplitudes of two oscillations are not equal, yeah, and there is some phase difference between of them. So we should obtain, we have to obtain the elliptical polarization, yeah? So let's try the amplitude of this one. We make smaller, and a little bit phase difference for the second wave, yeah? Okay. This one, the phase difference is very sensitive for a difference. Okay. Yes. So this all I said was about the sensitivity of the ratio between of amplitudes and the phase difference between of two oscillations. So in another wave, polarization is very sensitive to any disturbances in these ratios. So the first conclusion, so this tool is very sensitive to any changes in, for example, in biological objects. But we should know how to use these changes in polarization in order to make some diagnosis or something like that. So let's start with the Stokes parameters. This model experiment you saw, it's only calculation. But how one can measure directly from the intensity measurements this polarization and said that this one is linear, this one is circular, this one is even partly polarized, and this one is elliptical. So in early 18th, 52, Sir George Gabriel Stokes took a very different approach and discovered that polarization can be described in terms of observables using an experimental identification or definition. So, why? Because the polarization ellipse itself is only valid for a given instant of times. So, this ellipse is a function of time. With time, this ellipse will change. To get the Stokes parameters, firstly, one do a time average, integral over time, and a little bit of algebra also. And one can obtain this equation. So here you see the time, in this x, e, y. Here we deal now only with amplitudes, without time. And these two parameters, this one, this, and this one also, he called own parameters, his own Stokes parameters. The first one is a sum of amplitudes of these two orthogonal oscillations. The second one is the difference between of them. The third one and the fourth one, it's this kind of combinations with the phase. this initial phase also. Okay, let's return to the polarization ellipse itself. So, and how Stokes parameters can be described in geometrical terms. Here we are. This is normalized Stokes parameters. A little bit later about this. The first elements is unity, in any cases, because it's a whole intensity. We can divide all the elements on this intensity and obtain this one will be will be a unity. The second one is a combination of cosines, where here we are with azimuth, and this one is, what is this? Ellipticity, or no, vice versa. This one azimuth, this one ellipticity. Thanks a lot. Okay, the third one, and the fourth one. Because when we deal with, for example, elliptical polarization, and we can measure the fourth Stokes vector parameters, we immediately, just after that, we will obtain the value of ellipticity of our polarization or our wave. The Stokes parameters after that can be arranged in a Stokes vector. It's not a real vector, but it's something like from the matrix calculation. So we have a matrix in different dimension, and we have a vector. It's a matrix with one dimension is unity, yeah? So this one is Stokes vector. This first element is a total intensity of light. The second one, how we can measure the second one? We should just adjust our analyzer, polarizer, yeah, polarizer analyzer on the output of our system with angle 0 and measure this intensity from a CCD camera, from a photodiode, from all you want. Measure respectively, just turn this polarizer analyzer at angle 90 degree and measure this intensity and calculate using MATLAB, because as I saw, so very many people, very many scientists are in charge in MATLAB, very closely charged. The second one, this one, is a difference between these two components, intensity. So this one is a measurable quantities, just intensity. What about the force parameters? Here it's a little bit, I can say, harder, because here we should make this intensity of right circular component and left circular component. So in this measurement, we should add the so-called optical compensator, namely a quarter wave plate, before the analyzer, and adjust analyzer on these angles here and here, and also just divide between of them. Stokes vector elements for a linearly polarization or a linearly polarized wave is the following, because we have only this one is unity, this one and this one is not equal to 0, and the fourth one is absolutely 0. Differences between of linearly polarized with azimuth of 0 and 90 degree is only this one will be unity, this one will be minus unity, and so on. For a circular polarization situation, when we have a fully polarized and circularly polarized wave, the second and the third elements are absolutely 0, and the fourth one is non-zero. For a fully polarized light, this equation is in charge. Here, yeah, it's divide. For example, if we deal with partly polarized light, so here will be less. Not equal, but less. Okay. Now, we're just talking about Stokes vector. So we deals with a field, optical field. We can measure polarization state of this field, and so on and so on. We can obtain even a topological distribution of different polarization when we use the CCD camera and as a detector. But what about object? What object did this perturbation in polarization states? So, together with Stokes, if light is represented by Stokes vectors, yes, optical components are then should be described with a Müller matrices in such a way. This is a description, a polarization description of output light. This one is Stokes vector of input light. In order to do this mathematical operation, this one converted to this one, we have to use this 4-to-4 matrix called Müller matrix. When all these elements connected with an optical property of our object itself. So, for example, for very simple case, this one, input light, output light. And here we have some rhombus, some lens, and some triangles from, for example, from different types of glasses. This one, element 1, 2, and 3. So the transformation of light can be described with this simple equation. But this Müller matrices should be written in reverse way. Yeah, you know. This is a main formula connected, this one also, connected with the transformation of polarization and even non-polarized light. We can use this, as it was said by Professor Calve, we have to use some formalism. We have to invent some formalism in order to predict what is the optical properties of object with measured this Stokes vector. We measure Stokes vector of the output after the object. We know Stokes vector as an input signal. For example, it's linearly polarized with azimuth 0 degree. And after that, we can calculate Müller matrix. When different elements, it will be said a little bit later, connected with some properties of object. It can be birefringence, dichroism, and so on, absorption. So, briefly on the basics of laser polarimetry. So, every polarization microscope allows us to invent, for example, crystalline objects, yes? But not everyone can give us a possibility to measure all the Stokes vector elements in order to calculate Müller matrix. So we deal with Müller polarimeter. So it can be constructed on the base of conventional polarization microscope, but it can be separately collected with necessary optical elements. You will see it next Thursday here. In order to measure, okay, briefly described, it's a laser source. It may be not a laser source, but wideband source, and after that you should use, for example, some narrowband interferometric filter in order to get some wavelengths you want. But laser, it's more simple. This is a collimator in order to create a collimated beam with needed collimation ratio. This one is a first quarter wave plate. The task of this plate is only to create a circularly polarized wave. Because the laser here, for example, it can be diode laser, yes? It linearly polarized. And when we, after that, by means of this polarizer, want or do some changes in illumination of in polarization of illumination beam, the intensity will decrease, yes, at some position. So in order to overcome this problem, we use this quarter wave plate. For example, if you have a laser with a circular polarization on the output, so okay, no problem. But this is more flexible system. This one, quarter wave plate, put it here, provides a condition of circular polarization for the object in order to calculate the force Stokes vector parameters. Object can be a slice of histological section, it can be dried biological fluid, it can be something, but this one is for transmission mode, yes? If you want to deal with a reflection mode, you only put this part of this setup at needed angle, and you measure all the same. The procedure is the same. Against quarter wave plate, analyzer, CCD camera, and the processing unit can be. So, in order to obtain in this system distribution of azimuth and ellipticity of polarization, for example, it's a so-called polarization maps used in CCD camera, yeah? You should only measure minimal and maximal intensity here by means of rotating analyzer 9. It can be done with, for example, step engines and so on. These two arrays, minimal and maximum. And after that, calculate these angles for corresponding angles of this analyzer for this minimal array. And after that, simply calculate the polarization azimuth by subtracting pi divided by 2, and the ellipticity, like arctangents of this ratio of minimal intensity to maximal intensity. That's all. So it can be done automatically. And some automatical polarimeters exists, but not with a CCD camera, but for a single beam, yeah, with only photodiode. So let's talk about basics of model description of structure and optical anisotropy of biological tissues. What does it mean, optical anisotropy? Because every biological object, almost every, except of fat tissue, is anisotropic object. So optical anisotropy is a difference in the optical properties of a medium as a function of the direction of propagation of optical radiation in the medium and of the state of polarization of the radiation. So one can separate amplitude anisotropy, so-called dichroism, and phase anisotropy, called birefringence. What about amplitude anisotropy? So crystals and the biological tissue is a polycrystalline structure, may similarly show absorption which depends upon polarization. So for different polarization states of illuminating beams, the absorption will be different. One can see the linear dichroism and the circular dichroism. Linear dichroism, it's a dependence of absorption for a linear polarization. Circular dichroism, it's a depending on absorption of circular polarization. What about birefringence? Asymmetry in crystal structures causes two different refractive indices. And opposite polarization follow different paths through the crystal. one can show the linear birefringence and the circular birefringence, or so-called optical activity. So let's start with some animations. How many times? Okay. Just look at the phenomenon. Okay, we start with linear birefringence and linear dichroism. Yeah. What about linear dichroism? It's you can see that red oscillation, absorption of late red oscillation is much more than, for example, for the green one. It depends on the azimuth of polarization. What can we obtain? This yellow one, cube, it's an object, our medium. What we will obtain on the, what we can measure on the output of this object, because this too is only projection of the whole polarization, yeah? So we'll obtain something like this strange curve, you know. What about circular dichroism? Okay. So you see also that the green oscillation is not absorbing, but the red one is. And the output total polarization, yeah, oscillation on the output of this object will be as follows. So we are talking about, it's not really two waves in a crystal, this one. We have some, because any state of polarization can be represented by combination of two, or linear one or circular one. So in the crystal, it can be ordinary, extraordinary, and this dependence in absorption is evidence. Okay, what about, let's start with linear birefringence. This is my, so we have these two oscillations, yeah, on the input, and one of them, for one of these oscillations, the refraction index is a bit higher. You can see 1.05 and 1.00. So if I choose the similar refraction indices, the situation we were talking about on the previous lecture. So, and only just a little change in refraction index will lead to creation of elliptical polarization on the output of this object. So we should something do with this in our experiments. We should know what we are measuring and what is the process in object brings these changes, yes? Okay, so briefly, here you can see a soft tissue structure. It's a transmission electron microscope of human skin, dermis, yeah? And this is the model, because every tissue, most of them, muscular and derma and so on, connected with the very first element in this, it's a glycine and predominantly amino acids. It forms the tropocollagen. The tropocollagen forms the microfibrils and fibrils. Fibrils forms the collagen fibers, and the collagen fibers form fiber bundle. So biological tissue reveals self-similar fractal structure as a result of growth processes here. And the very fresh publications about multifractal light scattering in tissues prove this theory in Optics Express and Optics Letters. Here you can see also, this one, it's fibers, collagen fibers, and this one also, but in this direction, yeah? Okay, let's start with the algorithm of Mueller matrix modeling of biological layer anisotropy. As we can discuss a little bit later, so there are following mechanisms: phase anisotropy and amplitude anisotropy, divided to optical activity or circular birefringence and linear birefringence. Circular dichroism and linear dichroism. What parameters can we measure? We can measure for this process polarization plane rotation angle, sigma, and the corresponding partial Mueller matrix for this sigma. We can measure phase difference, phase shift between the orthogonal component of amplitude, delta, and this partial matrix operator. Index of circular and linear dichroisms and the corresponding partial Mueller matrices. This one is Mueller matrix M of generalized optical anisotropy of our biological optics. This one we measure in our experiments, but we should know the influence of these partial Mueller matrices corresponding to the different optical activities in this object in order to, for example, to diagnose cancer changes on very early stages and so on, because cancer changes on early stage connected with this optical activity of molecules. So, and we can decompose this Mueller matrix. We should know, we have to know the processes of decomposing of this Mueller matrix in order to define these algorithms separately. Okay. Yeah, just a bit of matrix algebra for circular linear birefringence, for circular and linear dichroisms. Here you can see it. These parameters. Here, rho, this one, rho, it's an orientation of fibril in the tissue in every point. Delta, it's a phase shift that this fibril brings between of orthogonal component of polarization. Here, the values of absorption. So the generalized Mueller matrix is as follows. This is normalized Mueller matrix, yes, where this element is zero, is unity. What about the experiment? Experiment proof this situation. For the skeletal muscle tissue, or skeletal muscle, you can see this whole Mueller matrix, these Mueller matrix images. And no one of these Mueller matrix images is not zero, because it tells us about the presence of whole four processes in birefringences and dichroisms in one tissue at one time. But what is the information content of Mueller matrix element of all this one? How we can decode? We can measure this, but how we can decode all of these images in order to obtain some necessary information? So, due to the modeling and so on, this one of elements, it's a first line, yeah? This line is connected with mechanisms of optical anisotropic absorption. The second and the third line of this Mueller matrix is connected with the phase modulation of laser radiation on the background of optical anisotropic absorption. So the mechanisms are presented simultaneously in these elements. The last line, it's a complex information about superposition of mechanisms of linear birefringence and dichroisms. But in several papers about the decomposition of Mueller matrices and so on, of Lou Chipman and other scientists, one can divide some Mueller matrix invariants. This one and this one are connected only with a very high precision, connected only with the mechanisms of anisotropic absorption. This one, M44, connected directly with the face with the linear birefringence. And this one, delta M, is a combination of elements. This one, difference, and this sum of diagonal elements, difference between It connected with a tangents of 2 sigma, it's a circular birefringence. So, it's how much time? 30 minutes, yeah? Okay. So, this is quite microscopic images in polarization microscope of different type of tissue. You can see it. For example, tissue with ordered and disordered structure. Here, you can see this order, yeah? It's a myocardium tissue in coaxial and crossed polarizer analyzer. So you can see that in crossed polarizer analyzer, here we can see optical activity. Light changed, polarizationally changed, and comes through the analyzer. The same for a brain tissue in coaxial and crossed polarizer analyzer. This one, it's a photograph or CCD image of benign tumor adenoma of prostate gland tissue in coaxial and crossed polarizer analyzer. This one is a tissue with benign and malignant formation, so precancer, malignant formation of cancer of cervix uteri, adenocarcinoma. This one is my favorite. This one is blood plasma, crystallite blood plasma in coaxial and cross polarizer analyzer. It's a so-called biological fluid. And this one is a synovial fluid of a joint with rheumatoid arthritis in coaxial and cross polarizer analyzer. So we deal not only with some soft images, we deal with pretty nice images. So let's start about what can we do after the obtaining of these Mueller matrix elements. What is the procedure of processing of these images? Because image is not a diagnosis. And if it is possible to make some objective evaluation, not subjective, because you know about the final diagnosis, it's histochemical methods, when some very clever man or woman looking in the microscope and said, this is cancer, this is not cancer, and this one, I don't know exactly, but maybe you can see. And you see, yes, it's maybe cancer. Okay, the third one, the fourth one, and so on. So we tried to elaborate some objective mechanisms of evaluation. So we deal with statistic analysis. It's 4 statistical moments, so-called mean value or average, standard deviation or dispersion, coefficient of skewness, and coefficient of kurtosis. For example, if we have some, what does it mean, mean value? You know, yes? It's a formula. Standard deviation, it's a disturbances between mean value. What is the skewness? Skewness, it's some like a tilt from left side to right side. This is normal distribution, yeah, Gaussian. This one with positive skewness, this one with negative skewness. Okay, here we have, for example, this one is a Gaussian distribution. This one is with a higher kurtosis. This one is with a lower kurtosis. But the mean value is the same. You know, this is very sensitive moment, this one and this, because especially kurtosis. You get some 2 images with equal mean value. It's quite the same. But due to calculation of these higher order moments, you can evaluate some differences between them. It can be very small. Okay, the second one, it's a well-known correlation analysis and autocorrelation analysis. So, you know this formula, yes? It's a autocorrelation, it's a correlation of signal with itself. What can we do with this? For example, in order to diagnose So any azimuthically asymmetric distribution can be evaluated by correlation analysis in two perpendicular directions, x and y. Based on this, we use the following methodology of autocorrelation processing for the distribution of values q. Q, it can be Stokes vector element, Müller matrix element, and so on. Your signal here. Here we have this different correlation function and with different half widths. Here you can see, yes? It's quite the same, but not the same. And this asymmetry coefficient is this divided P max on P min, this one P max on P min, gives us evaluation. For example, we can compare between almost the same image, almost the same two images. For example, with malignant formation and with normal. So the half width of the autocorrelation function plays main role. Okay, we have told about fractality of biological tissue. Also, we can calculate the power spectrum density of our images. Here it's a model image, for example, is for Stokes vector of birefringent cylinders. This one is two-dimensional autocorrelation function, and this one is power spectrum density. Okay. Fractal analysis is based on the calculation of logarithmic dependencies of power spectra of values q, yeah? And further mentioned dependencies are approximated by the least square method in curves f. Due to the form of these curves, for the curve, this one, it don't shown here, but this one, it's approximation curve. So the distribution is fractal, distributions are fractal. When there is only one stable inclination angle exists within 2-3 decades of sizes changes. Distribution are multifractal when there is several stables, yeah? Inclination angles exist. And the distribution are random when there is no stable inclination angles. So one can use this approach independently of statistic and autocorrelation. Okay, we called these approaches statistic, correlation, and fractal. We call it multifunctional laser polarimetry, because not only one parameters are evaluated and described, and several parameters can be simultaneously described. And when one method is not very good for evaluation, the second one will be much better, for example. Because also, this one, I want to that you keep in mind. All the data and parameters Q presented in previous lecture, measured in previous lecture, need to be quantitatively analyzed. Okay, this is the message. Okay, the last one. Yeah, 20 minutes. Okay, it's more time to the question, maybe. So, it's principles and methods of polarization and Müller matrix mapping, finally. Here, this is a Müller polarimeter, so-called Stokes polarimeter, whenever you want. We don't speak about the procedure of measurement of Müller matrix. Stokes vector, yes, but Müller matrix, no. The illumination conditions. It's a linear polarization with azimuth 0, 45 degree, 90 degree, and right circular polarization. Analysis with respected azimuth of this analyzer is 0, 45, 90, and 135, or it can be minus 45, yeah? It's the same. And right and left circular using this plate here. This is a procedure what we will do next Thursday. For example, first step, set transmission plane of analyzer with the angles 0 and 90 degree. Here, measured intensity of 0 component. Here, measured intensity of the 90 degree. This is a calculation. Here we can obtain first Stokes vector element and the second one. The second step, 45 and 135, the analyzer 9. Measure two distributions and calculate the third Stokes vector parameters normalized on the first. And the third step is consists of measuring the fourth Stokes vector parameters, and we will obtain this one. Similarly, one can calculate other Stokes vectors for another illumination condition, because here, so let the problem beam will be linearly polarized with azimuth 0 degree. Here, the whole algorithm. This is Stokes vector calculation. This is Müller matrix calculation using these Stokes vectors elements. And this is the calculation of polarization parameters, or so-called polarization maps. It's azimuths and ellipticities of polarization. It's just for an azimuth of polarization, it's just you should divide the third Stokes vector element on the second one and do these arctangents. The ellipticity parameters, it depends on the fourth Stokes vector parameters. Here you can see the measured, experimentally measured and analyzed through this three approach, Müller matrix invariance of optical and optical anisotropy parameters. For a linear birefringence, you can see it here. This is just a histogram of this distribution, and this is a power spectrum of this distribution. This is a circular birefringence, namely optical activity is analogously situation. But if you could see here that this one is more regular than this one, yes? Because this power spectrum is more linear than this one, yes? So even just take a look on this picture. This one is linear for Müller matrix elements for linear and circular dichroism with the necessary evaluation of this. And here, the last table, it's for, this is possibilities of multifunctional polarimetry for evaluation of these Müller matrix elements. This is for calculated for statistic moments. These two is second and the fourth statistic moment for the autocorrelation function. And this one, D, is a standard deviation of power spectra. For two groups of patients, precancer and cancer states. So, and you could see that prostate cancer, and you could see that here, this is the balanced accuracy of the diagnosis, these diagnostical methods. And this balanced accuracy is on the level of 80, 75%. It's quite higher. It's near the gold standard due to the histochemical methods. Thank you for your attention, and all the participants are kindly invited to attend Correlation Optics Conference in Chernivtsi in September this year. You could refer this website. So thank you once more.